The system that you see in front of you is our ABFN. It's comprised of a setting head. This is our TMEH 200, Tucker Blind Head 200, and it's the head that's designed for blind rivet nuts. You see the feeder below. It's our next gen TF60. This is the latest technology that we're using for feeding of for stud welding equipment, Tucker plasma joining, as well as for blind fastening. And then the controller is shared between our ABF and our TPJ technology. The setting head is about 30 kilos. It is one of the smallest, if not the smallest setting head in terms of size on the market. It's comprised of 2 DC electric motors, so there's no hydraulics in the system at all. The general overview is the feeder is feeding a rivet to the part presenter. Part presenter comes in front. We're engaging with the nut through the spindle, monitoring to make sure there's no cross-threading taking place. This is our floating front end. The front end is capable of 1.5 millimeters of X and Y movement, and also 3 degrees off perpendicular. So panel to panel variance, application to application variance, we're trying to take up as much of the deviations between the parts within the tool, so that there's not expensive fixturing that's always required or optical system. So start to start cycle time is a little less than 7 seconds. The head we're constantly monitoring the position of the head. So we know if it has made its way into the panel at the tolerance or the threshold that the customer indicates. So if I were to set, there's already a nut in that panel. If I were to set one right now, it would throw a fault saying it can't reach its intended position.
A lot of the feedback that we're getting from our customers is they want to know whether or not that the fastener is installed in the panel in the application correctly. And as Paul just demonstrated there's already a fastener in the panel, and it will throw a fault. And then we're also going to demonstrate whether the panel is completely missing and simulate that as well.
So when there's no panel there, the head will stroke 100 millimeters forward. Again, it'll bypass the threshold that we've got set in the controller and throw a fault. So the fault is that, maximum distance was reached, and yeah, basically there's no panel for the tool to set into.
Now, I think another point of interest from our customers is what happens if that hole moves a little bit, either X or Y, and that the pre-hole isn't as repeatable as we would like.
So as I mentioned, the floating front end is capable of 1.5 millimeters around the center line and up to 3 degrees off perpendicular that it's able to float. But the important part is, in the application that the chamfer, the tip of the nut, is present. It makes the hole finding more robust. We can set with a fastener that doesn't have such a generous chamfer, but the better the chamfer is, the easier it is for the hole finding to occur. So,
yeah, the larger the chamfer allows you for maximum tolerance from the floating front end.
Correct. So yeah, what I'll do is I'll move it about 1 millimeter in X and about 0.5 millimeter in Z, just to get you an idea. So again, even a little bit of deviation in the panel, we're able to compensate for it with the mechanical floating front end.
One of the main concerns that our customers have is what happens if the hexagon pre-hole is altered or turned a little bit so that the points of the fastener are on the flats of the panel.
one of the important aspects of the tool is to ensure that it's easy to operate, but it's also easy to maintain. And one of the more common components that it needs to be replaced as a consumable is the drive screw at the tip of the tool that's engaging and disengaging with the nut. It's also providing the setting, transferring the setting force to the fastener.
Is there anything special about this drive screw?
No, the drive screw is a standard DIN 912. You can do class 12, class 10 grade. It's a standard length, standard head. It's a DIN 912 fastener that you can get from any supplier.
Perfect. So there's nothing patented in there, nothing that would drive up the cost. It's a very low consumable that we can pass that savings off to our customers.
Right. For maintenance mode, the plant can have after X amount of cycles, to throw a warning so that the operator is able to go in and make sure that they change the drive screw. So what we do is we move to a service position, and the entire front end comes out of the tool.
Now with this service position, it can also be done in the cell, or it can be brought to a service position outside of the cell, so you don't have to lock out and tag out, right?
Correct.
Perfect.
So nothing special with the screw, as we mentioned, standard length, standard head. You get the screw put back in. The entire setup is a quarter turn, so it's tool free. To change the drive screw, you lift this collar. It's a quarter turn, and the front drops out. Screw comes out. You put your new one in. And again, just a quarter turn to lock it in. You go back outside. We have moved to a home position, and the entire spindle retracts back up into the head.
One of the main selling points of our ABF technology is actually having the system here in our Troy facility. We can do customer demonstrations, we can do fastener validations, whether it's a hex nut, whether it's a round nut, whether it's a square nut, whether it's our nut, whether it's a competitor's nut. We can validate all of that here and provide a full system demonstration with the support of our engineering team.